starting at x equal to 0 and ending at x equal to r is nothing but a real number r. So if we consider here a real number r, and any vector which starts from the point x equal to 0 and ends at the point x equal to r is a vector. Here we see that the magnitude of this vector is equal to r. Now if r is greater than 0, the direction of vector is forward, whereas if r is less than 0, the direction of vector is backward. So here we see that r is equal to 1. So the direction of this vector is forward. Similarly, here we see that r is equal to 1. So it is negative, and hence the direction is backwards, this way. So if r is greater than 0, the direction of vector is forward, and if r is less than 0, the direction of vector is backwards. Now if we assume that a vector corresponding to a real number x equal to 1 is a unit vector, so this is denoted by the vector I. Thus the vector corresponding to the real number x equal to r is a vector which is denoted by r times I. So this is a unit vector, and when it gets multiplied by r, it represents a vector which is equal in magnitude to r, and it is in the direction of this unit vector. Now this unit vector is called as unit vector because its magnitude is 1. So we take any unit vector along the real number line, and when it is multiplied by r, it represents a vector r such that x is equal to r. Now similarly, if we have any vector x equal to r times this unit vector and y is equal to s times the unit vector, then x plus y would be r plus s times the unit vector. Thus if we simply add these two vectors, this is the sum of the real numbers r and s times the unit vector. So whenever we have vectors in one dimension, we can represent it as some multiple of the unit vector, such that this multiple represents the magnitude of the vector. Now vectors in two dimension. Now how to represent vectors in two dimension? Now let's look at this figure. If we say that we have any point px comma y, x represents the abscissa and y represents the ordinate. Now ON is a vector which is equal in magnitude to x, so this could be represented as x times the unit vector, and let's say that this unit vector along the x-axis is I. Similarly, we can have another unit vector along the y-axis, and let us say that it is represented by j cap. So this vector Pn would be equal to y times j cap. We have applied the same concept as we did for x-axis. Thus the vector On could be x times I cap, and this vector could be y times j cap. Now we know that this vector plus this vector is equal to OP vector, and hence OP vector could be written as x times I cap plus y times j cap. We have simply added these two. Thus if P is any point with the coordinates x comma y, thus in two dimension the vector OP could be represented as x times I cap plus y times j cap, where I cap is a unit vector along the x-axis and j cap is the unit vector along the y-axis. Thus this is the way of representing a vector OP in two dimensions. Now if we want to find out the magnitude of OP, then now let us consider this triangle. Now this is a right angle triangle, and hence ON square plus PN square would be equal to OP square. Now ON square is nothing but equal to x square, and PN square is equal to y square. Thus OP would be equal to under root of x square plus y square, and OP is nothing but the magnitude of the vector OP. Hence the magnitude of OP would be equal to under root of x square plus y square. In two dimension we have represented OP as equal to the components of this vector along the x-axis and the component of this vector along the y-axis, which are x times I cap and y times j cap, and the magnitude of this vector OP is equal to under root of x square plus y square. So we can visualize it this way. If this is the point P, which is x comma y, so this vector would be x times I cap. The magnitude of this vector is x. Similarly, this vector could be y times j cap, where j cap is the unit vector along the y-axis and the magnitude of this vector is y. Thus this vector would be equal to the resultant of these two vectors, which is x times I cap plus y times j cap. Now if we want to take out the magnitude of this vector, this is equal to under root of x square plus under root of y square. Now x is nothing but the coefficient of I cap, and y is nothing but the coefficient of j cap. Thus we can say that every vector in 2D can be uniquely represented as a linear combination of unit vectors. Thus we have expressed this vector as a linear combination of this vector and this vector. Let us say that we have got two vectors x and y. Now x could be written as a1 I cap plus b1 j cap, and similarly we can have another vector y equal to a2 I cap plus b2 j cap. So we have expressed this vector as a linear combination of two vectors I cap and j cap, and similarly we have expressed this vector. Now if we want to add these two vectors x and y, then x plus y would be equal to a1 plus a2 times I cap plus b1 plus b2 j cap. Thus simply what we have done is we have added the coefficients of I cap and added the coefficients of j cap. So x plus y would be equal to a1 plus a2 times I cap plus b1 plus b2 times j cap. Now the magnitude of this vector is under root of a1 square plus b1 square, and similarly the magnitude of this vector is under root of a2 square plus b2 square. Now let's try to study vectors in 3 dimension. Let us say that this is the x-axis, this is the y-axis, and this is the z-axis. Now we have added another axis, which is the z-axis, for 3-dimensional study. Let us say that I cap represents a unit vector along the x-axis, j cap represents a unit vector along the y-axis, and k cap represents a unit vector along the z-axis. Now consider this triangle. We have OC vector, this one, we have CD vector, this one, and we have OD vector, this one. So OC vector plus CD vector would be equal to OD vector. This is the triangle law of addition. Similarly, we consider this triangle and we have this as OD vector, this as DP vector, and this as OP vector. So OP vector would be equal to OD vector plus DP vector. Now from this we write the value of OD vector here to get OC vector plus CD vector plus DP vector equal to OP vector. So OP vector is the sum of 3 vectors, that is OC vector, CD vector, and DP vector. Now OC vector is nothing but z times k cap, CD vector is nothing but x times I cap, and this DP vector is nothing but y times j cap. So OP vector would be equal to x times I cap plus y times j cap plus z times k cap. Thus we can represent any vector OP in 3 dimension as a linear combination of 3 vectors, which is x times I cap plus y times j cap plus z times k cap. Now if we want to find out the magnitude of this vector OP, then this is equal to under root of x square plus y square plus z square. It is very much similar to the vectors in 2 dimension, just the difference is we have added another axis, which is the z axis, and so any vector is represented as a linear combination of 3 unit vectors. Now if we have got any 2 points in 3 dimension, let us say that P and Q are such points, and the coordinates of P are x1, y1, z1, and coordinates of Q are x2, y2, and z2. So if we have got 2 such points, then the vector QP would be equal to x1 minus x2 times I cap plus y1 minus y2 times j cap plus z1 minus z2 times k cap. Thus it is the difference of the x coordinates, this is the difference of the y coordinates, and this is the difference of the z coordinates of these 2 points. Thus QP vector could be written as x1 minus x2 times I cap plus y1 minus y2 times j cap plus z1 minus z2 times k cap. So this is the way we actually represent any vector in 3 dimension. So most of the times we will be studying vectors in 3 dimension, and so we are going to use this notation of representing any vector in 3 dimension. Now we have already studied what are collinear vectors. Any 2 vectors A and B are said to be collinear if they are supported on the same or parallel lines. So if they are contained in the same line, then such vectors are called as collinear vectors. Here if the line of support is parallel, then the vectors may be parallel or anti-parallel. So for collinear vectors we need to have the same supporting line. If this line of support is parallel, then the vectors may be parallel or anti-parallel. For such vectors we represent vector B equal to x times vector A. So if A and B are any 2 vectors and are collinear to each other, then we write vector B as equal to x times vector A. Here x is any constant. Here this is a scalar quantity, and so B and A are any 2 vectors which are collinear, then they must be having the same direction, but the magnitude would differ. Thus that's why we multiply vector A with any scalar quantity x. Now we have just seen what are coplanar vectors. Now if we say that there are three vectors A, B and C and they are coplanar, then there is a relationship of the form vector C equal to lambda 1 times A plus lambda 2 times B. So we can express any vector C as equal to lambda 1 times vector A plus lambda 2 times vector B. The lambda 1 and lambda 2 are two scalars. So for any three vectors which are coplanar, we can express them as a linear combination of other two vectors. Now any two non-zero vectors which are non-collinear will constitute a plane. Now if we have any two vectors, then obviously they lie in a plane. So their sum or the difference will also lie in the plane. Thus we can say that if you have got any two vectors, then the sum or difference will also be in the same plane, or the sum vector or the difference vector would be coplanar with those two vectors. So once again we can say that if we have got any three vectors A, B and C which are coplanar, then we can express C as a linear combination of vector A and vector B. The next is the linear combination of vectors. Now any vector R, if it could be represented as alpha 1 into vector A1 plus alpha 2 times vector A2 and so on up to alpha n times vector An, then this vector is called as the linear combination of the vectors A1, A2, A3 and so on up to An. Here alpha 1, alpha 2, alpha 3 and so on up to alpha n are any scalars. Now these scalars could have a value equal to 0 as well, but not all of them are equal to 0. So any vector R, if it can be represented as this way, then it is called as a linear combination of the vectors A1, A2, A3 and so on up to An. Now let's try to understand the fundamental theorems. The first is for the two-dimensional case. Let's consider the two-dimensional analysis, and if A and B are two non-collinear vectors, then any vector R coplanar with A and B can be uniquely expressed as a linear combination of vector A and vector B. That is, there exists unique x, y such that R is equal to x times A plus y times B. Thus this is any vector R which is expressed as a linear combination of the vectors A and B, given that we are considering two-dimensional analysis and A and B are two non-collinear vectors. Also R is coplanar with A and B. So if any vector R lies in the plane of A and B, then it can be expressed as a linear combination of these two vectors A and B. Now if we say that x1 times vector A plus y1 times vector B is equal to x2 times vector A plus y2 times vector B, then x1 would be equal to x2 and y1 would be equal to y2. That is, the coefficient of vector A would be equal to the coefficient of vector A, and also the coefficient of vector B would be equal to the coefficient of vector B. Thus in two dimension, any vector R coplanar with vector A and B can be uniquely expressed as a linear combination of the vectors A and B. Similarly, let's see the case for three dimension. If A, B, C are three non-coplanar vectors in space, then any vector R can be uniquely expressed as a linear combination of A, B, C. Thus if we have got any three vectors A, B, C, these three are non-coplanar vectors, that is, they do not lie in the same plane, then any vector R in three-dimensional space can be expressed as a linear combination of A, B and C. So if we say that there are any three scalars x, y, z which belong to the set of real numbers, then vector R could be written as x times vector A plus y times vector B plus z times vector C. Now what are linearly dependent and independent